أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله وبركاته. Very good morning. Samchata to everyone. Could anyone respond so that I can really, so I can start the lecture. So thanks you, Paul. Also, you are very consistent in, responding, in class. Yeah, thank you very much. Okay. Before we start the lecture, first I would like to say invitation again to join my class today, Monday, 13th of December 2021. Our class is 1 hour class from 10 a.m. to 11 a.m. inshallah. And we are going to talk about new topics on the, fluctuation in speed and energy. So, Shukramullah, we can meet again today. So I already, posted the notes, the slide notes in our group. So please check your notes. So anything you can't catch up or anything that you lost, perhaps you can check on your note. And together that with that, you also have books with you. You can turn books, your book on page 206, which is on fluctuation speed and energy. Right? So before we start anything, I would like to share with you what are basically the keyword, perhaps if I may say, the fluctuation and spin energy. Many books written by the scholar, typically in European scholar, they do not mention about fluctuation and spin energy. They are mentioning about flywheel. So if you want to look at other topic or other information regarding this topic, you can look under flywheels. Okay, under flywheel. Or some is variables variable input and outputs talks. So different book has a different title, but basically they are basically discussing the same thing they are going to look or going to discuss today. Very familiar, a very famous one is if you look at the books written by the Indian scholar Kurmi, yeah, they call it, Kurmi call it as flywheel only, a very thick book, I think 100,000 over pages. So one of the topic is flywheel. So you look at that, topic. So many example and also information regarding the topic they are going to deal with today. Yeah. My books or perhaps then my notes is basically a part of what they are being discussing about the partition and spin energy. This is basically based on the topic that are going to be in our syllabus. So many more topic, yeah, many more subtopic. It is not included in my books. Yeah, okay. So that is one thing. So if you can go to this one, yeah, as usual, if you follow my note, basically I will start with knowing what are the thing that we're going to do or what are the thing that we want to look for, our task basically or objective basically. So one foremost, you're going to look for the fluctuation. So everyone know about fluctuation. Fluctuation simply mean that the thing will be varies. So what are the varies? Speed and also energy. Why varies? Because there's no equilibrium position, isn't it? There's no steady or steady condition or steady state condition. So they must be fluctuating below and above one's line or one level. So what are the level we are going to look the one later on. So the thing they have to understand is what are the thing that fluctuate is spin energy. Likewise, what you're doing in kinematic, if you found that the velocity is keep fluctuating because the velocity the fluctuation of the speed is basically or velocity will be basically based on hurdle, friction, so or perhaps when a vehicle climb a hill, for example, or go down a hill, for example, you found that the velocity is keep changing, isn't it? So you know that when velocity keep changing or fluctuating or varies, you found that another form will be contribute, which we call as acceleration. Same thing here. When you know that the speed is fluctuating, so what are the things we're going to look for later on? Yeah, or when the speed is fluctuating, energy also fluctuating because this speed and energy basically come together. If you look at the equation, for example, these two parameters basically in the equation. So how sure are we whether the thing will be fluctuating? This is based on this one, turning moment diagram. This turning moment diagram. Some book called crank effort diagram. If you look at book written by Kurmi called turning moment diagram. You look book for Hinkle and Simpson, for example, or Balachandran, they call it the crank effort diagram. It is basically the same thing, yeah. So crank effort diagram because the diagram itself is creating or created by the crank. You know what crank is? Crank is connected to the connecting one and also connected to the piston. Typically, we are talking about we are talking about internal combustion. It's not only that, crank also connected to another and any other which can be also rotating. Okay, so one be internal combustion engine, crank also connected in other any reciprocating part, typically on motor, for example. So likewise, I did mention earlier, it basically come to you turning moment diagram or crank effort diagram. Okay, so it's basically the same. Okay, okay, now we move to this one. So you can turn to page 1206, chapter 5 in your books. You found that basically this is the input motor. If you can see my cursor, I pointed to motor, and you have a generator here. And the thing, the motor shaft and also generator shaft will be connected or attached by or fitted by coupling, to coupling, typically universal coupling. And on the coupling itself, after coupling and before coupling toward motor and generator respectively, you found a flywheel. So this flywheel play a major role in contributing steadily or performing a good condition for this system, so that the system are running or operating steadily. So there is no speed which keep fluctuating. Okay. So our aims now is to look for flywheel here basically. So basically we're going to look for what is the flywheel, torque, when run by the motor, for example, or run by the internal combustion engine, for example. Yeah. So these are the things that we're going to look for. Turning moment diagram, sometimes we call TMD. Uh, the other one is flywheel and application. The application will be on two parameter. Yeah, one will be constant and variable input torque. You have the input coming from motor or perhaps coming from the internal combustion engine. So there are two input here. One be motor, the other one is internal combustion engine. Of course, motor will run or drive the motor. Milling, forging, so on and so forth. So many machine that run by the motor. On the other hand, you have the input not coming from the motor, internal combustion engine. So the internal combustion engine can also run some other parameter in the engineering appliances, or engineering devices, for example. Then we look for constant and variable resisting or friction torque. Some call resisting, some call friction torque. It is basically the same. For example, if you have the input coming from motor and the motor run the machine, for example, the machine. Let's say the machine will be the drilling machine. So the drilling machine will be efficient to the motor, isn't it? So the drilling machine is a friction to the motor. But when you run the machine itself, the machine also has the friction. Talking about drilling, for example, so it basically is basically what coming from the friction basically coming from what type of material you want to be drilled, for example. Let's say you are drilling mild steel comparing to the stainless steel. It is so obvious that you need more energy, isn't it, to drill mild steel, sorry, to drill a stainless steel rather than mild steel. Or you're drilling wooden, for example, compared to steel base. So wooden is much more easier compared to wooden space. So these are basically coming from the friction to the motor, isn't it? So you have our idea here is basically how to design a flywheel, so that the system will be run. Otherwise, if the system keep changing, when you're drilling something, the hole that you drill is not so smooth, or perhaps you're drilling milling, for example. So the surface that you are drilling is not so smooth, so it be rejected, for example. The other one would be when you're talking about the internal combustion engine run by generator, for example, isn't it? So internal combustion will keep fluctuating the energy, the input energy or the input torque, because you know well that the internal combustion engine basically what come from the what four parameter from coming from the suction, induction, compression power or exhaust, isn't it? Induction and suction is basically the same. So you have also because the internal combustion engine connected by gearbox, isn't it? So the input is basically keep fluctuating depending on what gear you are connected. So we are going to look for that, why the constant input and also the variable input to run the constant friction and also the variable friction. Then we're going to put fly. here. So flywheel, as we all know, that flywheel is basically storage energy. It's a bank basically, isn't it? It's a energy storage or storage of energy. Huh? So what is the function of flywheel? Is very easy. When you're talking about energy storage or storage of energy, it's basically what it will store energy when it's excess, when so many energy or so much energy, so excess will be stored energy. Then when the system need energy, it will be delivered energy or dissipating the energy. So the system now will be very what balanced now. Okay. The other part is the application toward of the what we're going to look for is this one, yeah, two application. One be coming from the internal combustion engine, as I mentioned earlier. Doesn't matter coming from SI or CI. This one, the SI is spark ignition. This one is combustion ignition. Okay, compression or combustion ignition. The other one is motor drive machine. Sometimes we call MDM. So the SI or CI is basically, if you're talking about the engineer, yeah, you're basically talking about engine run by the petrol and engine by the diesel, for example, or diesel engine or petrol engine. Yeah? Okay, this one is the turning moment diagram. So you need to know what is the turning moment diagram. So turning moment diagram. So if I can share with you, let me stop sharing this one. I'm going to share with you. Hold on a bit, yeah. I'm I'm going to open up one blank file here so that you can easily understand what is basically uh, the meaning of turning moment diagrams. I hope you have this one. Yeah, you have the blank share this one. You will have a new display, the empty display or the blank display. You got it, class? You got it? Yes or no? Thank you, Go. Yeah, thank you, Go. Okay, now, what I'm intent to share now with you is to define what is the turning moment diagram. This is very important because why? Because if you do not understand what is turning moment diagram, you basically cannot do the whole topics. So first, let us now start with what is the turning moment diagram. So I got something it's not running or functioning well here. This one now. Okay, turning. Oh, okay, turning moment diagram. This one, yeah. Sometimes we call crank effort diagram. It is basically the same or crank effort diagram. So remember this one. When you're talking turning moment diagram, so you have a x and y axis. So the y here is basically torque must be in Newton meter. On the other end, for the x here, it must be in theta in radian. Radian is unitless, isn't it? So whatever you have here is basically what area under the curve, area under the curve, which will give you this one multiplied by this one is t theta, and that is known as work done. So this is what work done. Or sometimes because the work done unit is Newton meter, we can also tell this one it is not also or it is not only work done, can also put in terms of energy is t theta. Okay, so in conclusion, the turning moment diagram must be in the form of torque versus radian. But sometimes, because we actually want you to, to think a bit regarding the turning moment diagram, we provide you some other parameter. It is not in theta. We provide this one in Newton meter, correct? But this one do not provide the theta, but instead we're going to put you this one in second. So area under the curve this one is not work done because you are Newton meter second, isn't it? We are talking about if you're talking about um, we are talking about power, for example, this must be Newton meter radian per second. So this one you have to convert. You have to convert it to become theta. How to convert it? It's not very difficult. You've done this one a lot of time. Theta is equal to omega t. Or sometimes you forget about the equation. Now don't worry. You know this one in radian. This one is radian per second multiplied by second. So you're becoming radian. So you convert this one by multiplying by omega. What is the omega? Omega is obviously the velocity. What type of velocity? Is the mean velocity. How do you mean velocity? Because the omega mean is equal to the omega max plus the omega mean, the smallest one, divided by 2. Okay, so as for today, not as for today, as now, you have to understand that turning moment diagram must be this one or second. So that is about turning moment diagram. Of course, the turning moment diagram representing turning moment diagram. This one representing what? Representing motor, for example. So many type of motor. Representing also internal combustion engine. So many type of internal combustion engine. Earlier I did mention about SI and also CI, isn't it? To depend on what type of internal combustion engine we are dealing with. On the other hand, we are also mentioning about turning moment diagram also representing what? Representing machine. So many machine I did mention earlier just now, coming from punching, milling, drilling, so on and so forth. So these are all represented by the turning moment diagram. Okay, but if you look at for motor, for example, yeah, for example, let's say you think about, okay, let's see now motor. Let's see now motor. So motor is the input, and motor drive the machine, for example. Let's put the machine is a milling machine, for example, milling machine. Okay, this one motor, this one is milling machine. Okay, so this one is a motor drive machine, for example. So you know well that this one have turning moment diagram. You also have a turning moment diagram. It cannot be because you want a system, isn't it? It is a system. If you construct a schematic diagram, for example, yeah, schematic diagram, motor, it will. This one is couple again. This one is the milling machine. I don't know how to draw a milling machine. For example, this one is milling machine, yeah, correct? For example, yeah. So you know this one also is a milling machine, for example. How come in one system there must be two turning moment diagram? No, it must be only one turning moment diagram. Only one turning moment diagram for a system. For a system. What is a system? Must be input and so that is why many turning moment diagram representing two parameter. So therefore, turning moment diagram representing two parameter. What are the parameter? They must be what? Input torque, input torque. The other one is the output torque, output, yeah, output torque. Two parameter. Of course, in here we are talking about motor drive machine just now. The input torque coming from the motor drive machine, isn't it? And the output torque coming from the milling machine just now. So in conclusion, you must have one single turning moment diagram, E in Newton meter. This one in, let's say in radian, for example. So input torque coming from motor, which we do not know. Let's say this one input coming from motor. And you must have another, what? Another graph. Okay, so you must have two parameter or perhaps two graph in one turning moment. This one is motor. This one is sorry, I put the same graph on one same parameter. This one is supposed to be okay. But remember, yeah, remember in any problem, so many problem, they do not provide you the two parameter, the two line or the two graph. They provide you only one graph. So you yourself have to confine or have to define another graph. So here today I'm going to share with you how to, to get another graph, which is not disclosed by the one that give you problems. Okay, so stay with me, inshallah. Yeah. Okay, that is one. So that is all about turning moment diagram. Okay. Then we try to move. We will move and oh sorry, we are not talking this one. Yeah. Let me come back to this one. I'm going to stop sharing. the other engine. I'm going to go back to the PowerPoint. I love to use PowerPoint because there's animation. So really hope that when you have a animation, you don't feel bored. Otherwise, you are just watch the static diagram, isn't it? Or static figures. Okay, this one is the flywheel. This one is the internal combustion engine. Okay. This one is I already mentioned about turning moment diagram. I really hope you understand what is the turning moment diagram basically. Yeah. So this is the turning moment. Turning moment. This is what we've been doing. No, we've done here earlier in our internal combustion. Sorry, in our balancing of internal combustion engine. When you multiply with this one a certain parameter, it becoming torque. This one you multiply by what? You multiply by certain parameter, they becoming torque. We are not going to do this one in detail. I'm going to explain to you why. I'm going to explain to you how the torque is basically generated in internal combustion engine. Okay, same thing for this one, internal combustion engine, as I mentioned earlier. So this one is fluctuating, keep fluctuating over a period of time and need to be controlled, need to control it. So you might be keep asking me why we need to control the engine so that the fluctuation of speed between the higher and the lower mode will not be so high. The reason is why if you have the higher mode and the lower mode is so high, for example, the engine have tendency to stop or to die. So we need a certain level of margin, we call it margin, 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 to ensure that the maximum speed and minimum speed is not so big, so the margin is so small. So when the margin is so small, you find that the engine will run very steadily. This one I did mention earlier just now about the SI and also CI. You can read on your own. This is talking about internal combustion engine, guys. Let's take a look at here. So this is our concern. This one, flywheel. This is our concern. The rest is not our concern. Our concern is all this one, the flywheel. Why? Because the whole thing, the whole arrangement from cylinder 1 to 4 will be generating power, isn't it? Then you have connected to flywheel. So this flywheel will play a big role to ensure that the engine running very very smooth, and it will keep absorbing energy and delivering energy when required, at the period of time when this keep operating, while the engine perhaps doing work, for example. How it's doing work, for example, if the engine the car, for example, running with level surface, so there is no work to be done so much. But when the car keep climbing a hill, for example, then you keep what you have to play with the gear, isn't it? Or you have to engage gear 1, gear 2, so on and so forth, because what you know that the lower gear will give you higher speed, sorry, higher torque. So that is why you need this flywheel to ensure that before you disengage and engage gear to gear, it will enough energy to ensure that the engine will not stop or die. Okay, this one is how it's work. Basically, this is the animation. If you look at the top left, top right animation, this is the actual one. When you have the at the right left one, is the actual one flywheel. This one the actual one. Yeah. Of course, you have your engine. You cannot see because it covered by the casing. If you want to see the one, you have to open up the casing or dismantle the casing. Yeah. Again, this one is the animation just to share with you flywheel, how the arrangement of the flywheel. Yeah. This one just in bigger, in bigger picture, so that you can basically see how it works. Look at the crank, this one crankshaft, look at the flywheel. The one is same rotation, even though you found that the crank is so small, but the flywheel is so big. Okay, when you know this one, then you, of course, you need an analyzer. There are two, if you observe very careful, here you have the ignition cable. The ignition cable will go to the distributor. So you want to know how much energy or perhaps how much torque will be generated by the engine. You have to pick up the signal. You pick up the signal from one cylinder to another cylinder and attach to an analyzer. So it will be displaying something like this one. How are you going to see this one when you do tuning, TUNIAG, in bahasa call it penjajaran, it's a tuning. Tuning is to ensure that the energy generated by the engine is very good enough to avoid loss of energy, for example, or jerking, Jerking. The engine keep jerking when you found the energy is not enough to run the engine is not enough to run the system. Huh? Okay, look at here. I didn't mention about just now. You have what? You have two speed. One is the lower speed, the other one the higher speed. They provide you here engine speed 900 by 2000. I think your diagram that you get is not put it what 500, isn't it? So they want is another example. You do another line in your notes. Put it here. Is taken from 900 and 2100, and you have the result of 1533. Yeah, 1530 here. Then you make a line here. So this one will be what you call as T mean. You call as T mean. So it will be keep generating system below T mean and above T mean. So you need to know the T mean here, because so when the system run at T mean, the system or the engine will not die or stop. So look at the graph. The graph is very difficult to calculate, isn't it? You need to what? You need to do integration, for example, area under curve by using all the charging or all the worms, second worm or third worm, isn't it? So very difficult for you, the integration, yeah? So we are not going to use this one because our aim is now one, our aim just now is to look at what is the work done generated by the system or looking by the area under the curve, isn't it? So we might be considering the graph is so smooth rather than have a very inconsistent graph or random graph. Okay, so don't worry about this one just to share with you that in analyzer they provide you as such, but the analyzer have capability to read or to measure or to calculate area under the curve by trigonometry expression. Here we are not going to do that one. We are going to do some other parameter, but very, very easy compared to what you have in the actual things. Okay, this one is more what call it, more logic, isn't it? It's easy for you to calculate because in terms of sine or cosine, you can integrate this one to look at what is the area under the curve. So whatever this one, you have the actual thing that you can represent it by this one. So you have what? You have suction, compression, working, and also exhaust. And this parameter, sorry, this activity, the four activity occurring very fast in a split of second or within the eyes of blink of eyes. So look at here. We have the suction, compression, working, exhaust. Now let me ask you now. If you look at the graph itself here, can you verify what type of engine is one? Four-stroke engine or two-stroke engine? By looking at the graph here, can you tell me this is four-stroke engine or two-stroke engine? So yes, how do you know it is four-stroke engine? How do you know? Yes, because I have 4 pi here. Remember 4 pi? Theta is equal to 720 divided by n. 720 is equal to 4 pi. So this one is belong to four-stroke engine. And you found that when you have 2 pi is representing two-stroke engine. Because why? Yeah, because in the system it will not be mentioning this is basically four-stroke or two-stroke engine. You have to look at the very careful what are the given parameters. Typically on the y and the x-axis. And when you look at very carefully here, you found that, okay, the suction, compression, working, and exhaust, in many, many explanations talking about internal combustion engine, you found that there were only one area which is overshooting Tmin or above Tmin will give you power. The rest or will give you positive work done. The rest are negative work done because this one, the suction, they need what? They need fuel and also air, isn't it? Then this one compression, you need what? You need the combustion to compare, then to provide you working. Working will give you power. Working is also power. Then exhaust. So you found that all negative here, but only one parameter will be positive, which coming from the power stroke or working stroke. Remember that for the internal combustion engine, only only one only one area overshooting or above Tmin to provide you power. This one we call as positive loop. So in conclusion, anything that above Tmin here, what is Tmin just now? Tmin what we calculated here just now, isn't it? So any area that above Tmin will be considered as positive and below Tmin we consider as negative. Okay, but if you look at this one, the actual thing is very difficult for us to calculate. Here you have a tendency to calculate by using trigonometry, for example. the integration, double integration of area, this one will provide you a numbers or numericals. Okay, remember this one, yeah, for internal combustion engine. Okay, this one is talking about the motor drive machine. Many machines run by the motor, isn't it? Run by the motor. Some very rare you find that the machine run by generator. Most motor run by the most machine run by the motor. The motor will be inside here, which we do not, we cannot visual in bare eyes. Yeah, you have to open up the all the casing, then you see the motor. The only thing that you have to visualize here is the flywheel. This is the flywheel. This is another flywheel. The big one flywheel. This one is very old engine. Old machine. But the recent one is one. Even the flywheel, you cannot see where will be the flywheel. So this one is the recent one. The left one is the recent one. The right one is the old version of the machine one. Huh? And this one is milling machine or forging machine. Okay. So the motor will be here. So what will be the turning moment diagram look like? This is the turning moment diagram. Contributed by the motor and also machine. This one motor and also machine. Which you know that it will be presented by a straight line. Okay, this one, yeah. So of course, again, it's very difficult for us to calculate this one. In such manner, you need an equation, for example, to calculate this one. So we were going to simplify the whole graph here to become a very graph that manageable to calculate the area under the curve by using, simple equation. Okay, this one, the actual thing. I want you to see this one because when you work, later on, you found that the thing that we study in class is not basically in the real life of engineering perspective. So when you find, oh, this one is the graph is very difficult compared to what you have in class. Of course, because in class we are going to introduce to you how to use the graph. When you are going, when you are, you are engineer, you are basically what have to ability to read this one because you have the capability of looking this one using the analyzer to read or perhaps to calculate area under the curve. Okay, so if I give you this one in class, very difficult for you to calculate and it takes time here. So no point of doing that. Yeah. Okay. Now let me see this one. Okay. Now this one again, same thing. You found it very easy to calculate. From this one, then we simplify to become some other form which manageable to calculate the area under the curve. Rather than this one, it's very difficult, isn't it? So you will have as such this one. Okay. But of course, when you work later on, you will see this one. Then uh, I love to share with you. This also can be done to explain why the PV diagram is what you've done in thermodynamics. The PV diagram is basically what the PV diagram is basically generated by the engine, isn't it? So it's very difficult for you to calculate this one if you have this one. That is why you have to do this one, the simplification of the actual PV diagram. Again, the PV diagram also provide you work done, isn't it? Also provide you work done. So then here you had to do interpolation that make you easy to calculate the area under curve rather than as such here. So this is just to share with you what you'll be doing in other parameter in other subject is basically can also be used in terms of similarity of looking the graph for the under area and area under the curve. Yeah. Okay, that is the introduction. What we are going to do next. So now we are going to do a couple of things. First, start with turning moment diagram for simple cylinder double acting steam engine. Then for four-stroke engine, then you have multi-cylinder engine, then your motor drive machine. So you have two parameters. Sorry, two special application as I mentioned earlier. One is coming for the internal combustion engine, which come from the different type of engine. The other one is the motor drive machine, TMD and also ICE. This is one of the example. You can turn to page 102, 207 in your book. You found that it will provide you as such. This one is belong to what? Belong to single cylinder double acting steam engine. Look at here. Don't worry about the graph, yeah, at the moment. Just worry about how does the graph look like. Yeah? You look at Timin here. So this Timin is very our concern here because you are going to look for above Timin also below Timin. So in any internal combustion engine, any area above the mean you consider positive, any area below the mean you consider as negative, as what we discussed earlier. This one again, as what we done earlier, is talking about the internal combustion engine. It's exactly as what we done earlier. This one also same thing. This one to share with you is, this one is not coloring, this one is coloring. That's about it. Yeah, the difference of these two. This one, look at here. You have the multi-cylinder here, multi-cylinder. But remember, yeah, sometimes because due to the complexness of the graph, which unmanaged us to calculate the area under the curve. So we simplify the graph to become a manageable graph or meaningful graph to calculate the area under the curve. One of the example is the turning moment diagram here. Sorry, one example is the machine drive, motor drive machine for the punching press machine here. Look at here. You can easily calculate the area under the curve by using the what rectangle or square or triangle equation, isn't it? Rather than you have as such, for example. So this one is meaningful and also manageable to calculate the area under the curve. Because as I mentioned earlier, our aims now is basic one is to calculate area under the curve. Okay, next thing is talking about today we are going only to talk about the overview of the topics. Inshallah, when we meet again, we're going to look for details one, how the equation look like, how to use the equation, what is the parameter for flywheel and so forth. This is a flywheel. Everyone know about flywheel. Flywheel is basically a storage, a storage bank or tank to store energy. So that is one, yeah. Rather than it basically coming from the rotational kinetic energy. It doesn't matter whether you have the flywheel solid one, solid, or you might have a flywheel like what you have here. It's the design flywheel. We call it a design flywheel because you have a rim here. You might have internal and external or out, inner or outer diameter, or you have a web here. So you must have used different parameter or different equation to compromise the flywheel designs. Yeah. This is just to share with you the discussion of the parameter for the flywheel. You can read on your own this one. Same thing as this one. You can read on your own. I'm going to share with you. Yes, this one. The use of the flywheel. Look at here. This is what you have in book. This is what you have in the actual things. Look at the actual thing. This where is the flywheel? This one is the flywheel. The flywheel play a big role to ensure that the system will be run steadily. Look at here. This one is the flywheel for the energy storage. Look at the flywheel. This one, your flywheel, the electrical energy here run very smooth here. Or perhaps you have this one. This is the crank diagram, isn't it? Then it will be also look like as flywheel here. Then exactly they will provide you TMD very consistent, rather than fluctuating spike and so many spike. Okay, as I mentioned earlier, when you're talking about a flywheel, you have two parameter or two equations to be used. One be the easiest one, which is R equal to mk square, where you found the k now is the radius of gyration. The other one will be R equal to half mr square, where you found this R is basically the actual diameter. And this is the solid one, and solid flywheel. The top equation, solid flywheel. The bottom equation is for the design flywheel, where you found that the k will be the radius of gyration. Doesn't matter what will be the design look like. The other thing is the parameter that we concern is here. The b is the breadth. The other one is t is the thickness. This one is the arm is the radius from the center to the outer. These are the three parameters we are going to look for. This is all the actual type of flywheel, typically in engineering perspective, except this one, the smiley. Smiley is not the flywheel, yeah. This is another one for power generation, yeah. If you look at the power generation here, you will have as such this one, flywheel. This one will be running or rotating quite with high speeds to ensure that the energy generated or the energy supply will not be fluctuating. If you found your bulb, yeah, or your lamp, yeah, in your house, sometime blinking, sometime not blinking, isn't it? So it will basically not enough. Or perhaps if you go to pasar malam, pasar malam is the night market. You found that when the people use the generator to light the lamp, to light the light, isn't it? You found that when generator is not well functioning, the light will be what, sometime bright, sometime not bright, correct? That is what we say, that the energy keep fluctuating, and as the energy keep fluctuating, the light also keep fluctuating from brightness to the dim. So that's what we're going to look for. Or perhaps if you have the old bicycle, if you have an very old bicycle where you have dynamo. You know what dynamo is? The dynamo is attached to the wheel, and the dynamo has the very small cylinder and will attach to the wheel. When you cycle and you ride, it will hit the wheel, then it will give you energy, and it will light the lamp, isn't it? So if you stop, it will stop. It will you If you ride very fast, the light will be very bright. If you ride very slow, the light will be very dim. So you keep fluctuating because there is no flywheel. If you put flywheel, for example, yeah, but of course in electrical there is no flywheel. Basically, you call capacitor. So if you put capacitor in term of flywheel, so the capacitor will basically acting an energy storage. So you'll keep will keep what stored energy. When you ride very slow, they will disperse energy, and the light will still maintain as bright as when you run very fast. So that is the analogy that you learn, when you are, have a dynamo. Of course, today's there's no dynamo. You have a torchlight running by the batteries. Okay. This is the flywheel application, typically an engine and also typically in motor drive machine. You have this one. This one all in it flywheel running or fixing on the engine, internal combustion engine. Doesn't matter whether it belong to internal combustion engine of V engine, radial engine, or inline engine. Doesn't matter. As long as flywheel, we are talking about the energy storage. This one is a example when you have flywheel attached to the machine. The machine is listed here: punching press machine, lathe machine, milling, so on and so forth. So many machines here. So this one is just to share with you. You can turn to page 216 in the discussion of this one: flywheel in punching press. One with, one without. This one is without. You found that the hole here, or perhaps the finishing plate here is not very good, yeah, compared to the thing that when you have flywheel. Because when you have flywheel, the punching operation will be running very smooth, and you found that the surface is very good in finishings. This one is some other form of flywheel. uh, Leisure, typically, for fitness. This one for, you have a static bicycle or air bike, so on and so forth. And when we come back, inshallah, on Wednesday, we're going to look for this one. What is the variable and constant of input and resistant torque to be part of our, what do you call it, special application. Before we end our session, I would like to share with you this one last. This one is the input torque, of course, one the vehicle, for example. You have this one is all the input torque. The input torque of the internal combustion engine run the car or vehicle. You have the input torque coming for the motor, run or drive machine. Look at what is the difference now. Okay, now tell me, what is the difference between input torque coming for the internal combustion engine and input torque coming from the motor? Could anyone tell me? If you can answer this one, you really understand what we are be discussing, today. So, anyone? Then I will ask you about resistance. Focus on input. What you understand by input torque run by or generated by the internal combustion engine, and also what is input torque generated by the motor? Could anyone explain? Very brief one. You can write, or you can speak up. You can on your your speaker or your mics. Anyone? Hello. With me, I've got 54 candidates wish to be, inshallah, a good engineer. Could anyone, dare to answer my question? Tan, speak up. You want to speak? Speak up, please. Talk by motor when constant. Yes, thank you very much. A very good one. And your click, yeah, correct. It is very correct, yeah, guys. The input torque generated by internal combustion engine is basically very what? It's keep fluctuating. How? Because we keep engaging gear. Doesn't matter we are talking about automotive, sorry, automatic transmission or manual transmission. Doesn't matter. When you have the manual transmission, you have to what? You have to change the lever. To change the gear is basically to engage the gear one, gear two, gear three, isn't it? So when you keep engaging gear one to higher gear, the input torque we also keep on fluctuating. So in conclusion, the internal combustion engine generating variable input torque. The motor, when you switch on the motor, you find that the motor is automatically what? Generating constant torque. Okay, you have 3 more minutes. So now that's one. The other one. Could anyone tell me what is the difference between resistance, yeah, resistance torque coming for the motor, car, for example, automobile, and coming for the machine? Anyone? Perhaps Tan, Eng, Lim, Marcella. Those names, I call because they usually respond question in my class. Lim, Eng, Lee, anyone? Automobile, for example, what will be the resistance torque generated by the automobile? Could anyone give me? Resistance torque remain constant from engine varies the time, is correct? What about machine? What about machine? You can speak up, you don't want to write, yeah? We have 1 more minute, 2 more minutes before we end our session. If you don't want to answer this one, I think I will leave it like that and you have to, seek for the answer on your own. I really don't. Machine due to different machine remain constant. Sorry, Tan is not correct, Tan, yeah? Machine is not remain constant. Okay, I basically don't care whether you answer correct or not, as long as you respond my question. Yeah, okay, look at this way. Yeah? Okay, machine inconsistent, correct? Yeah, correct. Cool. So machine is basically what? Machine will provide you a varies or a fluctuating torque depending on what just now type of material to be cut. What else? How big the hole is if you're talking about drilling machine. If you're talking about milling machine, how thickness will be the level you want to be cut. That is one. Yeah, it keep fluctuating. So the resistance torque is keep fluctuating, varies. But what we're talking about vehicles, yeah, or automobile, yeah, you find that the engine will be running with capacity of 2.0, for example. It will remain as it is. That is the resistance. The bearing will remain as it is. The level of the road will remain as it is. Isn't what else? The hill will remain as it is. So the resistance coming for the vehicle is always constant. Remember this one. The resistance coming from the vehicle is always constant. The resistance coming from the machine is always variable. This one, the input torque coming for the internal combustion engine is always varies. The input torque coming from the motor is always constant. So these are all the parameters we're going to look, inshallah, in the next lecture. So any question before we end our session? This is the conclusion, yeah? Input torque and resistance pressure torque on page 209 and so on. When we meet again, inshallah, we're going to discuss this one in details. So as for today, we are basically come to end. So any question you would like to ask before we end our session today, class? Anything? No? Anyone? Anyone say yes or say no, please? Any question? Yeah, Nazifa. Thank you, Nazifa. Okay, so thank you, Chia Ali. Thank you. So So I think we come to end. Inshallah, I meet you again. Inshallah, next meeting, I'm going to explain to you in detail the spatial application of this one, and together with that, we're going to contribute, or we're going to look for equations. So with that, I end the session. Thank you for being with me. Thank you for enjoying. I really hope that you enjoy my class. With that, I end my session with Assalamualaikum warahmatullahi wabarakatuh. Stay safe, stay healthy, and also have a nice day. Thank you, class.